interrupt me. I will not mind.
Okay, great,
Okay,
fantastic.
wait, should I stop sharing the screen?
You don't have to because I can see that I have the option to just
Really? Zoom has
yes,
that option. Wow.
yes, just start sharing. Can you see my slides now?
Yeah. Okay.
Okay, great, perfect, good. Helen, just to let you know, for some reason, when I was joining the Zoom, I was asked to log in. I think it was for the first time, so I think we didn't have this option last week. So I'm not sure if it's just a different setting in Zoom or maybe something changed. But this is just to let you know because I guess that the other participants might be also asked to Zoom to log into Zoom first.
Yes, the
I'm not.
mission. There's a mission pop up when you yes.
Yes, exactly.
Okay, yeah. Okay. Got it.
All right.
But
But
where
anyway,
are you?
I'm in Warsaw. I'm in Poland.
In Port. Wow. What time is it there?
It's 5 p.m. So it's already
5 p.m.
afternoon.
Okay. Not
Yes.
bad. Okay,
And
it's okay.
how about you? Where are you now?
Huh?
Where are you now? What's
In Knoxville, Tennessee.
in Tennessee? Okay, nice.
Yeah. We are
So,
just
so it's
close
quite
to
yeah, it's
close
quite
to
early.
no, it's not early. It's close to lunch.
Okay, good.
Yeah, it's about lunch.
All right.
About brunch actually.
Yes.
It's okay. It's a pretty good time, you know. Is you're at 5 p.m. I'm at 11 a.m. Helen is in Boston, I guess.
Yeah. So it's
I'm
also
in
11
Washington, D.C.
in
Yeah, okay.
Washington.
Yes, 11 a.m. As well,
Mm-hmm.
right? Oh yeah, that is a good time.
Yeah. Anyway, it's a perfect time for
Yeah,
meetup for people from America and Europe and Africa as
yeah,
well.
yeah. There's the Africa. Oh yes. And Helen also told me something about she was considering the India time zone. Are there people attending this meeting from India?
Uh,
So some people from
some
India.
people, yes.
Oh,
There are
cool.
some. Yeah, not many. Majority is from the US, I believe, or US or
Oh, but
Canada.
that's really cool that
Yeah.
we can see people from
Yeah.
abroad and from far away. Yeah, that's really cool.
Yes. And yeah, so Helen, will we record the meeting as well? So I believe it will be recorded on YouTube.
Yes, I
Yes.
already did that.
Oh,
Right.
good. So yeah, so it's recorded and later people can watch it on YouTube as well, and then
Oh, okay.
the
Okay.
time zone is not that important.
Oh my
Good.
God, I will be famous.
You are already famous, so this is all good. Yeah, so Sriram said that it's 9:30 p.m. in the evening in India. Oh, good.
Oh, well, okay, it's not bad.
Not
Yes.
bad. Yes, I
Yeah,
agree. It's not bad.
let's say no one is not going just to
Good.
lose his or her sleep because of this meeting, probably.
All right. Good. Helen, I think we can start because it's already 3 minutes past 11 a.m. in Washington. All right, so the meeting is now recorded. So let's start officially. So hello, everyone. Welcome to our next quantum computing meetup organized jointly by quantum computing groups from Washington, Toronto, and Warsaw. My name is Pavel, and I'll be one of the moderators together with Dr. Sebastian Zając. Yeah, we have pleasure to host our great speaker, Dr. Vicente Leighton Ortega. And Vicente will today give us a talk about quantum computing in machine learning, navigating potential and understanding limitations. So as you can see, this meeting is recorded, so hopefully the video will be later available on our YouTube channel. If you have any questions, we've agreed with Vicente that we can make this event interactive so that you can raise your hand and then we'll try to interrupt and ask a question. There will be also a Q&A session at the end, so you can also post your question on the chat and we can also try to ask it later. Okay, so before we start, we would also like to announce our next event. So the next one will be in March about compiling resource-efficient programs with numerical instantiation. And then there will be a lecture given by Dr. Brett Green about Landau level phases of bilayer graphene. And then in April, Eric Reiter will give a talk about a serious challenge to quantum mechanics and its limitations. Then in May, Dr. Bruna Araujo will tell us about moving towards compactification of the many-body wave function using a bottom-up approach. And later in May, Dr. Ed Augusto will tell about quantum reliability, circuit susceptibility faults, and integration issues. And finally, I would like to thank our partners and sponsors for helping us in organizing this event. So as you can see, there are quantum computing groups from different regions. So I'm representative of the Quantum AI Foundation, Q Poland, and Warsaw Quantum Computing Group. So with this, I will stop sharing my slides. And Vicente, if you are ready, you can start sharing your slides, and we can slowly start. The Zoom is yours, and thank you for accepting our invitation.
Okay, thank you, Paul. Thank you, Sebastian, and thank you, Helen, for this opportunity to talk about my work, to talk about some topics, some limitations that quantum algorithms face when we try to implement them in real hardware. Let me see. Okay, can you see my screen right now?
Yes, I can see it.
Oh, okay. Yeah, there are some problems. There are some issues yet to solve when you try just to apply some quantum algorithms. The idea is to solve classical problems. The idea is to solve problems in industry using the quantum computer as an embedded system to the classical computer. There are different angles. There are some people that say, okay, I want to use just the quantum computer. I want just to produce pure quantum algorithms. But there are another vision to say, okay, the quantum computer is very good for some kind of tasks, and we can just take that advantage. And the classical computer is very good for other things. And then we have different embedded systems like GPUs, TPUs. We have clusters, and we have a optimal infrastructure in the classical picture. And we can just merge that with the quantum computation infrastructure and make something really good. That's one of the that's the vision I follow. I agree with that. I think the quantum computer in the near future is going to be an embedded system, a very good embedded system to the classical systems, to the classical computers. And in this talk, I will just go through different aspects. I will not go into too many details. I will not go to explain too many technical information. I will just give you some glimpse about what kind of things we can do with quantum computers, what are the problems, and what kind of solutions we propose. Okay, let's start first with the more or less the outline of this talk. I guess this is what I said already, just to see, for instance, what are the capabilities of the quantum computation, the limitations in terms of how good is the quantum computer in order to perform a task. Also, what kind of interface we are going to use to communicate classical instructions with quantum instructions, because we have to manage the quantum computer. We have just to control the quantum computer, and that control part, that managing part, is held by the classical computer. And now there is no any standardization about that. Everybody just propose their own way just to communicate to the quantum computer, and that is causing some problems, some problems in terms of translation, compilation, etc. I will talk about that later. Let's start, for instance, with a very broad concept. What do we want to do with quantum computers? We have, for instance, different applications. I call that transformative applications because it's something that you can solve in different platforms. Classically, you have numerical methods. Here, let me just use my. Here you have just numerical methods, and then you have different platforms where you can just run those numerical methods. But you have just to somehow encode your problem in order to be solved by a different methods. For instance, one example is when you want to solve the dynamics of a system and you have just to discretize the time evolution. So you have just to define what would be your time step, and by finite difference methodology, you can just solve a differential equation. That is one example. You have your information, and you have just to somehow find a way to translate that information into something that the numerical method, can solve. In the quantum picture, we propose different quantum solutions. We have different quantum algorithms, like the Shor's algorithm to find something. We can simulate quantum systems. We can just simulate the quantum evolution of a given Hamiltonian. We have also quantum annealing. We can simulate the state evolution of an Ising motor, for instance. But we need to translate whatever we have here in the classical picture. How we have to translate this into the quantum picture. How are we going to represent the data in the quantum computer? How the quantum computer is going to get that information? That is called quantum embedding. And that part is crucial because in the quantum embedding you can lose information. In the quantum embedding you can use a redundant number of qubits because that encoding will be not optimal, and then you will need a lot of qubits just for some information. And that is one part of the problem here. How you can just translate your classical information into the quantum computer, and also once the quantum computer has processed that information, how you can just get that processed information out of the quantum computer. And we have some limitations because we can only apply some kind of measurements. We cannot see the whole picture. We see just a projective representation of whatever is going on in the quantum computer. That is another point, how to extract information from the quantum computer. Now let's go and then let's expand a little bit what we had before. Here, for instance, we have some why we consider a quantum solution. There are different arguments. Because there is a speed up, because you can prepare a quantum state that is a combination, a superposition of different quantum states. So you are treating a lot of information in one object, and you just measure that object, and then you can just parallelize your execution, so to say. And that is something that in the classical computer is not really allowed. We can also, in the classical computer, if you want just to represent, I don't know, a transformation, you have just to define the transformation in terms of matrices. The matrices are really heavy, and then you have to use TPUs just in order to process big matrices. And in the quantum computation, if you have a matrix, you can propose a quantum operation that represents that matrix. And the quantum computer is that kind of operations are native in the quantum computer. So the quantum computer will not have any effort just to send that operation to be processed. So that's another point that we are looking for of using the quantum computation. Now, for instance, as I told you, the quantum computer needs an interface just to adhere. Sorry, we need this interface to communicate to the hardware. This is the interface. In the interface, you have just to at the user level, you have to propose some. You have to just to set some instructions. There are different quantum instructions called gates, and then you have to set those instructions, and then you have just to process those instructions, compile them, and optimize optimize your procedure. And this is a very critical because you will go to a quantum control layer. It means that your quantum instruction is going to be a physical aspect in your hardware. So that instruction you are sending to the quantum computer is going to be a signal to be sent to the hardware, and that the effect of that signal on hardware will represent your instruction. That is not easy. There is loss of fidelity. So when you send a signal to the hardware, hoping that that signal will represent whatever you ask, there is a mismatch always. And there is a problem there, depending on the platform. If you are using superconducting quantum chips, or you are using trap ions, photonic, or topological qubits. Every platform has a different way to produce the quantum operations, or the quantum gates, or the quantum instructions. And also every platform will have a different noise effects, because there's a different engineering platform, different environments, different classical connections to the hardware that produce some noise in the electronic wires, etc. There are a lot of things that we have to consider in order just to
Quick question.
Yes.
Yeah, if you hear me.
Yeah, yes.
I wonder if all these different solutions that you have on the right side of the slide,
yes,
do they have anything in common? Or can we imagine some things like to do hybrid between them?
Oh, yes, you can. Yes, you can somehow. There are differences between them. For instance, the Church algorithm is an amplification of a given quantum state. You don't know a quantum state, and there is a procedure to amplify that quantum state. You don't know. And simulate quantum circuits is just a way just to you have your Hamiltonian, and then you want just to produce the evolution operator of that Hamiltonian in terms of quantum gates, and then you do a compilation of that, and you just consider time resolution. In every aspect, you can just try to use the quantum computer, but this is not really, for instance, it's not really an exact numerical methodology. It has some range of tolerance. The way they have in common is how you can just use quantum operations in order to infer about something you don't know in the measurement outputs. But you can, yes, I haven't seen some combination of them, but definitely it is not out of the it's not impossible just to combine the different methodologies. I don't know if that answered your question.
Itamar, is it fine?
Yes, thank you very much. I think
Oh, thank you. Thank you for asking.
A lot to explore in this direction. And again, with the input and output, the question would be, one day there will be standardization of those input and output to make the user's life much easier to access.
That is a very good point. Actually, yes, that is a very good point. We are looking for an standardization where we don't have just to learn different ways for different applications. Must be one way. You need just to apply your quantum algorithm for a given application. That is a very good point. Thank you.
Yes, sorry to interrupt there. You know,
yes.
You're making comparison there between classical computers and quantum, and I've been using classical computer for large computation, particularly during CFD computation of fluid dynamics, which deals with millions of degrees of freedom models, and that's require really parallelization, which we tend to use thousands of cores. So I wonder with quantum solutions, how are you going to deal with this? So you will not have parallelization. So how are you going to deal with these millions of degrees of freedoms in our models?
Okay, that is a very good point. For instance, when you have, let's say, the Ising model, you have a lattice of quantum systems. Every node in the lattice represents a quantum system, and they interact to each other. And you can, for instance, encode a line of 50 elements, 50 objects, 50 atoms. You can encode that in a quantum computer because the quantum computer natively can load that information in a quantum state. What is different from the classical computer? The classical computer, you have just to, if you have too many qubits, you have just to use tensor networks and contract some of the tensors in order to handle the load of information in the matrices. But in the quantum computer, the operations can represent matrices. So you don't deal anymore with any matrix there. It's just an operation. It's a signal that you send to the quantum computer, and that signal is processed there. And this is how, for instance, the quantum computer could beat the classical computer, because our representation is through quantum operations. So, for instance, if you have to load a lot of information, you can just encode that information in a quantum state. It doesn't matter how big is that quantum state, because you can use 10 qubits, 20 qubits, you can use 100 qubits, and that will just store a lot of information, and you can prepare a quantum state with 100 qubits that will just at the same time prepare a superposition of different quantum states. So you can just carry a lot of information, and that is not represented as a matrix in the quantum computer. Remember, this is just a quantum operation. This is why, for instance, the quantum computer is probably is faster than, well, it could be faster than the classical computer. I said could be faster because we're still proving the supremacy of quantum computation.
Okay, there's one more question from Kevin. and then we'll move forward.
Yeah,
Oh
so
yes. Yes.
question basically this is that if you have classical data, all of it's being done significantly better with tensor networks, dequantized algorithms, and variational quantum algorithms. When do you think there will be quantum data as a viable option for quantum computing, quantum computers?
Oh yes, that is a very good point, because there are different pictures. You can use the quantum computer to treat classical data, or use the quantum computer to treat quantum data. And the quantum data, for instance, is when you have a material science, you have a correlation, you have you want to discriminate if some quantum states are symmetric or non-symmetric, and you want just to check that, but you have too many quantum states, and then you need some variational principle or some learning procedure just to see what kind of states are even or odd. And in that kind of scenario, you see quantum information being treated by quantum computation, quantum computers.
So did you have a time frame for that as far as quantum data?
Sorry, what?
When you could use quantum data on quantum computers, that seems to be the viable option, because the other ones, you know, tensor networks and dequantized algorithms, they rely on classical data. So the only true advantage for quantum computers appears to be in using quantum data.
Yes, there are different, yes, because yeah, as I said, there are different angles. You can just find some utility of the quantum computer. One of them is using quantum data, because you can know it's very difficult to treat that quantum data in the classical computer. You have just to use tensor networks, and you will lose some entangling resolution when you do that. But when you use, for instance, the quantum computer, you can just pass all the information, the quantum states as they are, to the quantum computer. That is a very valuable use for the quantum computer, and that will really exploit all the benefits of use a quantum computer.
Thank you.
You are welcome.
Yeah, how does this quantum classical integration protocol work? Just an example, you can suggest some example.
Yeah. I was going to talk about that.
Yes.
Yes. This is okay. Thank you. You just remind me what I was going to do. Thank you. Yes, that part, the quantum classical integration. Actually, you need somehow integrate the classical computer with the quantum computer. Remember that is the only way you can send signals to the quantum computer to be processed, and then you get some information out of the quantum computer. But when you measure the quantum state, and you just do some classical post-processing, because you get some signals, and then you have to transform those signals into zeros and ones, right? And then you have just to procedure with some classical step. Yeah, I mean classical, that a classical computer is going to do that. But in this part here, it's just the integration. When you get this classical information from your quantum computer, zeros and ones, what are you going to do with that? And then there are some hybrid algorithms that uses the quantum computer as embedded system. And then, for instance, if you want, yeah, I'm going to talk about that in a couple of slides, but I can introduce that already. For instance, when you want to reproduce probability distribution, you have a distribution, let's say, and you want just to reproduce that distribution. You get the information, you just can produce the samples to produce that distribution using the quantum computer. For instance, that would be one way. Another way is if you want, if you have a Hamiltonian, for instance, a molecule, and you can encode the evolution operator of that Hamiltonian in the quantum computer, you can just compute the mean value of the energy using the quantum computer, right? And then you can just see how is that value, and find what is the best configuration you have to send to the quantum computer in order to minimize that value. And that procedure, finding what is the best configuration for the quantum computer, is done by a classical computer. I mean, is done by a optimizer, a classical optimizer, and that's the integration. And then the classical computer find the best configuration for the quantum computer, and the quantum computer computes the mean value. I will talk about that in a couple of slides to give you more information about it.
Okay, I see that one more person would like to ask a question, but I'm not sure, Vicente, do you want to ask a question now, or maybe we can just move forward and then come back to a question? Or
how many questions?
I see there's one more question, so let's agree.
Okay, let's go ahead with the last question.
Yeah. So Jordan, please.
Hi. So the data loading problem and the quantum classical framework. Your collaborator presented with us, Daniel, Dr. Caldino, I believe you pronounced the last
Claudino. Name? Claudino. Yeah.
Well, tell him we all said hello, one, and then two, he brought up he worked on the XACC framework, and that's one area, I think, for this integration. But in the literature that I'm researching, there are quite a few people working on this problem right now. But it's a highly complex problem, and there's a lot of variables involved. But is that something it's currently working on, you guys, right now still, or is this something that was put on the shelf?
Yes, sir. There is regarding this integration. It's not easy because you know that the quantum computers are getting bigger and bigger. we are getting 100 qubits. The plan is to get 1,000. The amount of information you will handle requires a lot of classical computational power, right? And this is why we are working in the integration of the integration between clusters, high performance computing, classical computer, and quantum computation. So the cluster is going to manage the quantum computer, because the number of parameters you have just to send to the quantum computer is huge. You cannot just really use your normal laptop or your desktop. So we need just to integrate this with HPC, and that integration is not easy because there are different levels. There, for instance, the cluster is also a high demand architecture, so everybody needs to use a cluster. So there is a queue to use a cluster, but the quantum computer also has a queue because it's a highly demand operational device. And there is one problem there, because once you have access to the cluster, probably you will not have access to the quantum computer. Okay, when you have access to the cluster, you have access to the quantum computer. How they are going to communicate each other? And one way is using different interfaces like XACC, the one we built here in Oak Ridge National Lab, and there are other representations. There is a second one called quantum intermediate representation. We are working with them as well. Yes, there are different ways you can just tackle this problem, and we are working on that.
Thank you.
You are welcome. Okay, let's continue. Okay, this is really, really fun. I like when people just can interact, and I hope I'm answering all the questions.
Yeah, as for now, all of them. Good. Let's continue.
Yeah, yes. Okay. And now, for instance, let's go to a particular case, this picture here is going just to answer a previous question about the integration classical quantum computing. And for instance, on the left-hand side, we have this is really simple. I'm sorry for the simplicity I'm imposing here. I know this is really simple, but I just want to capture the broad idea what a machine learning algorithm will do. And then you just have an observation here, you have a problem, you have some physical observation, you have some data, and then you want to process the data. But the data as it is not useful. You have to extract some valuable information from that data, and then you have just to apply some feature engineering just to extract information. The one technique is the principal component analysis, or there are other techniques where you can just extract valuable information, where you can see correlations between the data, and then once you have your information, you can just send that information to a model training. In that model training, you just fix parameters in your neural network in order to see that the neural network is doing what you want that neural network do for you. And once you have the model, you have an outcome, and then you can test that model using new data. I'm sorry, this is quite simple. I know there are more layers and layers and layers, more modification, more things to consider. And I apologize for this simplicity, but this picture allowed me just to introduce how we can use quantum computer to help to help this process. And then we have something similar. We have some classical data. We go and then extract some features. But now we don't want just to use those features in the classical computer. We want just to embed, just to encode that information into the quantum computer. There are different ways to encode that information. You can encode that information into the parameters of a quantum circuit. You can encode that information into the amplitudes of a quantum state. You can encode that information to the phases of the quantum state. You can do several things. There are different procedures. And now, once you have the information encoded, you will use your model. Your model in this case is not a neural network. Your model is a quantum circuit, and this is the quantum circuit. These guys here represents quantum operations applied to a quantum state. You start here with a quantum state, and then you apply first this layer, and then you apply second this layer, and so on. And then these operations are parameterized. It means that you can just control how they control their performance. And there are two different kind of operations. One is local operations that applies only one qubit, and the second one are entangling operations that apply to 2 qubits or more qubits. Just for this simple picture, I will consider just 2 qubit entangling operations. And so these entangling operations will produce a richer quantum state, and you can just repeat this procedure several times. Every time you will say, okay, there are different layers and layers to make a richer quantum state. I mean, with rich quantum state with more information. And then you measure that quantum state, and then you pass the output of that measurement to a classical optimization. For that, you have to define what will be your cost function, how you are going to process that information. And then you have to define what is the cost function. Then you allow a classical optimization to minimize that cost function. And this guy is done by a CPU, classical processing unit, and that CPU will propose a new set of parameters to the quantum circuit. And then you start again this loop until some criteria meets. I don't know, the number of loops or the level of the cost function. If the cost function reaches something, a value very close to zero, you just say, okay, I'm done. It's ready. The model is ready just to be tested. And then once your model is ready, you can just use new data if you want to test the model, and you go to the feature engineering, the quantum embedding, and test the model. Now, this is a crucial problem here, is the decoding, because your model is giving you some measurements, and then you have just to evaluate those measurements, extract that information, or get some information from that quantum state you are preparing using that quantum circuit. And that is a challenging problem. How you can extract information from the quantum computer? Depending on the number of qubits, that would be a nightmare. If you have just one qubit, okay, just perform just a couple of measurements. But if you have 10 qubits, you have to perform something like 2 to the 10 measurements. Something really crazy. Scales very bad with the number of qubits. And that is a crucial problem here. How you can extract information from the quantum computer. And this is just the global picture. How you can use a quantum computer in a hybrid algorithm when you use a CPU, a QPU together in order just to solve a problem. Is there any question about this slide? Okay.
I'm not sure. So there was
I have a question.
yes,
I
there was
have
a question
question.
from Davis. Yes. Mhm.
Yeah. You mentioned about the quantum embedding.
Yes,
So,
sir.
how, at which level will need quantum embedding? And
yes.
which problems will quantum embedding solve?
Oh, yes. Let me just, for instance, usually when you have your information, just when you get your features, right, you get some vectors. For instance, you get something like this, something like some vectors. Here you have n features, right? And then I want just to represent this information into, let's say, into a quantum state. And then a quantum state is something like this: alpha 0, the first state, plus alpha 1, the second state, 0, 1, and so on. So you have to somehow make a transformation between these entries and the alphas. And the way is just you normalize this vector. Let's say this is the normalized vector, and now the entries of this vector could be a good candidates for the alphas, because the alphas must be too normalized. Remember, it is a quantum state. And then these guys, this transformation, when you normalize that vector, could be a good transformation to embed the information stored in this vector into the amplitude of a quantum state. And now, once you have your quantum state, you can just process that quantum state in the quantum computer. This is the entry, your quantum state, and then you can process that quantum state and do, I don't know what kind of tasks you are going to do, but you can just, for instance, see if that quantum state belongs to a set of, or not, just for discrimination, or if that quantum state is very close to a distribution or not. Yeah, depends on your problem. But this is a crucial step, how you can just take this information, this vector, and represent this vector in a quantum state. I will talk about this later with the MNIST data set, and I will explain you how we could embed those images into a quantum state.
Okay, we have 2 more questions. So
Okay.
do you want to answer now? Okay. So maybe Raja first.
Yeah. So when you talk about the transformation, if we are desiring to have physical variables, so transformation should be unitary between those vectors.
The transformation between the embedding transformation between this guy and this guy.
Yeah, it should be unitary.
Conformal. No, yes, should be. It can be conformal, because you can
the vectors are normalized, and the variables, physical observables are real. Then I think the transformation should have that unitary character.
Yes, this one is just one way to see that. But for instance, we in a world where we did a couple of months ago, we used, for instance, a stereographic projection in order to go from this space, from this space to this space. This is the Hilbert space, and then if you want just to use this transformation, you can. And then we saw that we can use any conformal transformation, because what we want to do is conserve the angles but not the sizes. In this guy, for instance, this is the simplest way. When you just normalize the vector, is the simplest way, and that way to encode the classical information is not really good, because what happened if you could have something like that. You can have this feature, for instance. You can have just the null element of your space. There is nothing that avoid that. You can have the null element of your feature space, and how can you just encode that into the amplitude? And we saw that problem. Or you can have something really small. Let's say it mustn't be 0, but something really close to the null element, and then that will have, and then this kind of encoding procedures will have a lot of problems with that numerically. And yeah, then we tried different protocols, and one of them is the stereographic projection, and then we saw, okay, it's enough to conserve the angles. I mean, some more or less the relative position between the points, but not the sizes. The size can be modified.
Yeah. Okay.
And of course, if you normalize the vector, is the easiest way. I know is the direct way, but has some issues. So has a lot of issues. A second issue is what happens if you have a B1 proportional to B2. These two guys are going to be represented by the same quantum state if you normalize them. And that is another problem. There is not a unique correspondence between the features and the quantum states.
So there are degenerate states present in the system then.
Sorry, what?
So there are degenerate states present in the state given system.
Oh, excuse me, I didn't hear you very well. Can you give
So I'm saying it's degeneracy comes into play.
I think I also don't understand clearly. So Raja, maybe you can try to reformulate your question a bit.
Yeah, so I'm saying there is a degeneracy if your vectors are proportional to one another.
Degeneracy, I think.
Yeah. Yes, there could be, yes, or a quasi generance. Yes, but because there must be no proportional, but something really small, very close, and that will be problematic.
Yeah.
Okay.
Thanks.
Okay, thank you.
We have two more questions, Vicente. So
okay, let's do it very quickly.
Okay, so Jordan, please, your second.
This is more of an engineering question. So are the advancements with using logical qubits helping with the quantum control layer compared to using systems with physical qubits? Because they're really increasing rapidly right now. the number of those logical qubits. So is that whole process, is it easier to solve this problem here with the data loading and the control layer, or is it more of a burden to solving all of this?
Oh yeah. When you define your logical qubit, is a different layer here. For instance, when you do the quantum embedding is going to be applied on the logical qubit. So there must be a transformation between the just to produce that logical qubit, and that is an extra layer in this procedure. And that, yes, that would be problematic. But now, for instance, Continuum is using a very nice protocol where you have 10 physical qubits per logical qubit. That's quite doable, because if you have 100 qubits, it means that you let me just remember that five physical qubits. I guess it was 5 physical qubits. It was something really a few qubits. I'm sorry for the misinformation. Let's say a few qubits. And yeah, of course that will bring an extra layer, because you need just to transform that logical qubit into something that you want to represent. Then that is an extra layer, right?
Thank you.
Okay,
You're welcome.
And there's one more question from Sabari Krishvaran, so I can read it, but maybe he can also unmute himself. So how does we compare the performance of quantum neural networks with classical artificial neural networks? Is it the number of parameters required, or hidden layers, or another way?
Oh man, you just asked a $1 million question. Oh my God, that is a very difficult question. Thank you for asking that. It's really difficult. It's very interesting. Yes, it's a lot of people is working on that because it's not easy compare apples to apples. In the neural network, you have how should I put this? You have a very good neural network. You have a very optimized protocol in terms of neural networks. It wouldn't be fair to compare the best neural network with, for instance, this kind of parameterized quantum circuits. This is just the basic one. We are just starting that field. So if you want just to compare neural networks with parameterized quantum circuits or quantum neural networks, you have just to make it even, but in the basic format. I mean, a basic neural network, for instance, like the RBM, the restricted Boltzmann machine, with just one hidden layer, would be comparable with something like this. And in that respect, you can somehow say, okay, the restricted Boltzmann machine has somehow the same parameters as the quantum neural network. And you can just make that kind of comparison, but it's not really easy to judge who is better. We did I have a word about that in finance. We just compare the restricted Boltzmann machine with the data with the Bohr machine. The Bohr machine is something like this with a quantum circuit, with a parameterized quantum circuit. And yeah, there are some advantages and disadvantages when you use the quantum neural network, but it's really easy just to bring a metric that will provide a judgment who is better. It's not easy.
Yeah.
Thank you.
Got it. Thank you.
Okay.
No problem.
So actually, we have at least one more question. Would you like to answer now, or maybe we can proceed and keep some questions for the end?
Okay, yes, let's proceed because
yeah, otherwise we'll not finish.
But thank you very much for the questions. It has been really funny. I hope I'm answering all the questions very well. Okay, let's continue here. This is the quantum circuit Bohr machine. And what happened here, for instance? We have parameterized quantum circuits. Okay, sorry. This is the parameterized quantum circuit, right? And we have a target. This is our target here. This is a distribution we want to replicate in the quantum computer. And then this distribution corresponds to the bars and stripes configuration of 4 digits. This is some images you see here. This is an image of 4 bits, 4 pixels. 4 pixels, and then you can just translate these 4 pixels into bits. And then you can just, in this order, you can say, okay, the first image corresponds to the first bit, the second one, for instance, this one will be the first bit, 0, this one will be the second bit. Oh, sorry, I guess I have a better picture of that. Hello?
Yes, we can still hear you.
No, I have, okay, yeah. Oh. Yes, I got a problem with my iPad. That's why my iPad is refreshing. Oh, I'm so sorry. Yeah, it's back. You see here, this is just the how we encode these images. And then what happened? We know, for instance, in this example, we know that this configuration appears once when every cell is empty. The second configuration appears once as well. There are 6 configurations, so the distribution is 1/6, and there are 6 elements. And this is the distribution. 0 corresponds to empty, and 15 corresponds to full. And we want just to reproduce this distribution using the quantum computer. And what we do is just to set different layers. Every layer has some parameters. In every layer, there are rotations, entangling gates. We just made a combination of general rotation. Let's entangle the first qubit to the second qubit. We have any strategy, let's say. We just consider, okay, let's communicate all the qubits through entangling gates, and let's after that rotate all the qubits with some parametric operations. And then there are different layers, and then we measure this guy, and then the measurement is just we can extract from the measurement the probability distribution of the quantum state we have prepared. And when then we see how far is this distribution to the distribution we want to see, and we just measure the distance between these 2 distributions. You can measure the distance between these 2 distributions in different ways. We can just pick one of them, which is the Kullback-Leibler divergence. Just give you how much information you have in difference between these 2 distributions, or how much information you have loose if you want just to see this distribution compared with this. And then and then you can just insert that distance into an optimizer, and then the optimizer will decide what parameters are going to be tested in the next iteration. And then we have here the optimizer will update the parameters of the quantum circuit. The quantum circuit will produce a new quantum state. We will see how is the distribution of that quantum state and how far is that distribution from the target. And then the optimizer will decide again what kind of parameters are going to be used in the next iteration, and so on. And this is just the learning path, the learning procedure here. And then you see, for instance, here in the first iteration, the distance 1.6 here is very high. Kullback-Leibler divergence of 1.6 is saying, okay, they are not even close. They are quite different. And then the optimizer will pick different parameters, and then in every iteration, you can see how the distance decreases. The distance decreases depending on different factors. We use different layers. We use different topologies. There are different ways you can connect the qubits. In a line topology like here, in a star topology, all the qubits connected to one common qubit, or all to all. And then depending on the connectivity, depending on how many layers you are going to use, is the performance of your learning process. This experiment, this algorithm was tested on a ion trap machine in Maryland, and this here you can see what is the theory, and the experiment. The theory, what is the meaning of that is when you just run a simulator and you simulate the execution of a quantum computer on a classical computer, just to see if your quantum algorithm will do what you expect. And yeah, and then this is just the simulation in green and purple, the experiment. This is one clear example of hybrid classical quantum algorithm, when you want just to reproduce a classical distribution using a quantum computer. Is there any question about this?
Okay, let's wait. I don't see any question on the chat, but maybe
Okay.
people will ask. So.
Okay, let's continue.
Okay.
And then, for instance, yeah.
Yes, go on. And
okay,
yeah.
Let's continue. Then remember that, for instance, in this part, we just consider a bunch of rotations and a bunch of entangling gates. We didn't really use a structured way to design the parameterized quantum circuit, because we were just testing the pipeline of the algorithm. We were just testing, okay, how we can reproduce mimics distribution using the quantum computer. But in the next work, we were designing the parameterized quantum circuit, and then we found that, okay, why do we need to prepare a standard quantum state? You know, the quantum state has some amplitudes, and these guys here, these amplitudes, are complex numbers. And the phase of this complex number, let's say these guys can be written like this. And this phase will never be seen in the probability distribution. You will never see that phase in the probability distribution. That information is loose. You never will. If you want to see the phase of that or those elements, you have to apply a very complicated procedure. But you never see that thing. That thing is that the phase is really not contributing into the distribution after you measure the quantum state. So we just decide just to prepare quantum states with real amplitudes. So these guys are real. So we don't need too many operations to produce just quantum states with real amplitudes. We need just one kind of rotation. It means that decreases the number of operations we will need. So this is just the design we came when we just use real amplitude quantum states, only with that kind of operations and entangling operations. And then we have another problem, because we were using a different machine here. We are not using an ion trap machine. We were using a superconducting quantum computer, and we face a different problem. It seems that when you measure the qubit and you see you do nothing on that qubit, you should see in the output only zeros, right? Indicating that the qubit is in the ground state. But when you do that in a superconducting qubit, you see some output 0 and some at 1. So indicating that the qubit is in a superposition between 0 and 1, and that is not correct. And that is called a readout error. So we have to mitigate that. It's just a mistake when it's just a mistake internally in the process when you just take the measurements and convert those measurements into zeros and ones. That procedure has some mistakes, and those mistakes are reflected in your output, in your experiment, and then you have just to correct the re-out correction, the re-out, sorry. And then we design a protocol just to correct the re-out in superconducting qubits. And for instance, here, this is very nice. We could get this very nice distribution. Pink is the experiment, and gray is the expectation. And then you see, for instance, there is very close. Believe me, it's very close. Imagine coming from here to here is a very nice output. And nowadays it's even better because the error correction is not really a big deal. There is a little bit of error correction. A little bit of re-out error. Let's say something like 3%, 2% of your output is re-out error. And it's not really a big deal, and the results are getting better and better. The quantum machines are better. This is what we did in this work, and then we were just looking into the design of the quantum circuit, and then we saw that the design of the quantum circuit is critical if you want just to use the quantum computer as an embedded system to prepare samples, to prepare a quantum state you want to see. And now, for instance, let's say, and then we in that line of ideas, we were studying how to prepare an arbitrary quantum state. And then we start with the fundamental building block, which is the 2 qubits. Then you can start from 2 qubits to n qubits, but the fundamental one is 2 qubits, and then we started with that. Okay, how can we just prepare an arbitrary quantum state with real amplitudes? And then we came with this configuration here. This configuration connects the ground state 0. I'm sorry, this is 0, 0. This ground state to any quantum state with real amplitudes in the Hilbert space. That is the configuration you have to use. And then if you want to just to connect two different quantum states, you have just to add an extra rotation here, and you can connect 2 different quantum states. And then it means that block is quite powerful. You can go anywhere in the Hilbert space, so you can prepare any quantum state. Here is the paper. You can see more information about this on that paper. And let me just proceed with one application we use in using this configuration. Then we can scale this up for more qubits. If this is using just 2 qubits, we can use 3 qubits, and then we can scale this structure to 3 qubits, to 4 qubits, to 5 qubits, etc. And then we were thinking, okay, we have the ability to prepare any quantum state. We have a very expressive quantum circuit, parameterized quantum circuit. How can we use that? And then we were thinking about QGAN, a quantum generative adversarial neural network. And then that was our target. Okay, let's do this in a QGAN. In a QGAN, you need to represent very well the real data. You need to generate new data that looks like so real. So you need a very good generator. And we have a way to produce any quantum state in that Hilbert space. So we can use that generator there. And then let me just introduce to you the generative adversarial neural network, how that works. There are 2 agents. The first agent is a discriminator. The discriminator the goal of the discriminator is to discriminate real data from fake data, and then you train that discriminator with these two sets, because you already know they are already labeled, and then you can train the generator just to recognize real data from fake. And that is a supervised learning procedure, so you already know who is real and who is fake. And now, after you have a very nice generator, you go to the when you have just a very nice discriminator, you go to the generator. And now the generator, using the discriminator you already trained, the generator is going to produce new data, fake data, that look like so real. So the generator will try to fool the discriminator, and then this is a second training step. Train the generator. Now the generator is better. The discriminator can't see the generator, and now you enter in a new loop where you start over training the discriminator with the new generator. And this is why the procedure is called adversarial, because these guys compete until the generator is so good, is generating so good fake information that the discriminator can't just see the difference. When you get that position, you stop and say, okay, the generator can generate new data. How can we just implement this or use the quantum computer into this algorithm? Okay, let's start with the quantum embedding. We have then let's start here with what kind of data we are going to use. We are going to use the MNIST. The MNIST can be every single image here can be represented as a big vector. The vector is quite big. If you want to use just a few qubits, it's too big, and then you can just extract some information from those vectors, and then you use the principal component analysis. That is a way also to compress the vector, and you can just use principal component analysis and reduce the dimensionality, so you can feed the features after the PCA into a quantum state. And there is one way is, as I mentioned in a couple of slides before, you can just normalize the vector, right? But there are a lot of problems with that. You can have equivalent elements, and then those equivalent elements will be represented by one quantum state. You can have very, very small elements, and those small elements will have problems here because you are divided by the norm of that vector. And then, okay, we have that problem, and then we solve this problem by introducing the stereographic projection. The stereographic projection is quite straightforward. Actually, this typo here is this guy here. You can identify these 2 points. This is a circle. Let's say you can this can be a hypersphere, but just for visualization, we can just reduce that to a circle. There is no any problem with that. And then this point, the circle is identified with 1 point in this line, in this real line. And the identification is 1 to 1. So any point on the circle has a representer on the line. So the line is my classical data, and the circle is my is some data I can easily can be easily represented by a quantum state. Why? Why is that? Because this guy is already in a sphere. So the norm of this point is 1 as the amplitudes of a quantum state. So I can just make the identification of this point on the sphere to the amplitudes of a quantum state. And this is how you can describe that. You go from the Rn, I mean vectors, go to the hypersphere, and from the hypersphere to the Hilbert space. And for that, you use this parameterized quantum circuit. This is the parameterized quantum circuit we started in the last slide. This parameterized quantum circuit can prepare any quantum state with real amplitudes. This is the structure. So you can just, if you have this point, you can have a quantum state, a set of parameters that can be produced, a quantum state that represents that point in the circle. So we have the elements in the real data, and we have quantum states that represent those elements one to one. And we don't have any problem if this guy, if in the real data there is something really small, or we don't have any problem if the two elements in the real data are similar or are equivalent. We don't have that problem. The equivalent, sorry, similar, no, equivalent. They are proportional. They will be represented by different quantum states. So we have solved that problem about the embedding. And now, for instance, we had just the quantum embedding, and now the quantum generator, we will use exactly the same parameterized quantum circuit to generate fake data. And now the discriminator, for the discriminator, we consider an extra qubit here. We consider an extra qubit, and we consider this is the input state, and this is a parameterized quantum circuit, and we measure this extra qubit. Depending on the output of that extra qubit, we can decide if the input belongs to one set or belongs to the another. And this principle works more or less like the classical picture when you have, for instance, here, where one set of elements and another set of elements, but they are very difficult to discriminate, and then you send these elements to a higher dimensional space where you can just discriminate those sets very well. It's the same principle, but with quantum circuits. And this is more or less a little picture. It's a simplification, but it's going on there. Actually, you can draw a high dimensional Hilbert space. I just use the Hilbert space for one qubit, but the concept works. And then, for instance, here is when you just embed, put that quantum state in a higher dimensional Hilbert space, and then here you can only apply unitary transformation. So you cannot just separate these guys from each other. You cannot squeeze. You cannot expand these guys. But you can do, the only thing that you can do is just rotate these guys around, and then you can rotate the red spot in a position where you see a positive measurement of the Z mean value. That's the only way you can do, and then this is how we design the discriminator, and then we have the generator, the discriminator, and this is just the first step when you just train the discriminator, and this is the training for different quantum circuit executions. And then, for instance, here we have after in green is after 25 epochs, 25 evolutions, 25 loops, we have trained the discriminator and the generator. And this is the part of when we train the generator, and this is the cost function of the generator per epoch and per quantum circuit execution. And this is the output. Once we have the quantum circuit, we reverse the procedure, because we are in this, we have quantum states, and then we take those amplitudes and put those amplitudes in the hypersphere. From the hypersphere, we send that to the real plane. In the real plane, we apply the inverse of the principal component analysis, and we get the images. And this is the produced data. This is fake, and this is the real one for using just 4 qubits. yeah, this is one application how we theoretically we can use the quantum computer to generate handwritten digits. Is there any question about this? Yes.
Yes. Is this description of the discriminator
Yes, sir.
is actually a very effective way of classification?
Is not the best effective way of classification. There are better ways to classify data. You can use support vector machines, for instance, and then you can in the support vector machine you can use the quantum computer to create the kernel. The support vector machine is classical, totally classical, but the kernel is built by using the quantum computer. That is a one very effective way because you can just separate non-linear from you can use non-linear frontier between the sets and separate the sets even if the frontier is non-linear. This guy here is we use that because it's very simple and the frontier between the frontier we were considering to discriminate was not really non-linear, was really flat. So we use this kind of procedure because of the simplicity, not because it was the most effective one.
You
see, for instance,
about the circuit?
Yep. Yes, what this circuit?
Well, it's more general about circuits. Like it's known in classical computing with the Arduino and Strawberry Pi, we can have dedicated hardware circuits to do repetitive operations and connect them to the major computing tool for efficiency. Can I think about something like this, about the circuits that
Yes,
are
sir.
done in quantum computing?
Yes, sir. You can think something about that. Imagine that the quantum computer is just generating samples for the classical one. As you are using your Raspberry Pi just to generate something for your computer. You can think, okay, I need the quantum computer just to generate samples, or just to produce the kernel, or just to just for a given task. I need just the quantum computer for that.
I don't have to build it every time from scratch.
Yes, exactly. Yes.
Reusable.
Yes, you can just use some modularity. Then you say, okay, I don't have just to. I know that the quantum computer, I provide these inputs and it will give me these outputs. And yeah, that's right.
Okay, thanks.
Is there any other question about?
Yes, there's one more question. Question from Chunk. What is the neuron in parameterized quantum machine learning?
What is the what?
Neuron.
Neuron.
Mm-hmm.
Neuron in parameterized quantum circuits.
So I believe that what corresponds to neuron. I believe that this is what Chunk had in mind. But Chunk, maybe you can unmute yourself and clarify. Or what corresponds to the neuron?
I don't know. I will say something a node, a parameterized node. In this case, would be the rotations or the parametric operations.
Yeah, I agree.
I would say that.
Good.
That is a very good point. I haven't thought about that. Thank you. It's very nice when you see that the questions is a very good way to learn new things, right?
Yes. There was one more question about advantage of entangling gates. So what advantage do the entangling gates offer in quantum machine learning? I'm not sure if it has been answered or not, but maybe you can.
Oh no, I haven't talked about that entangling. Yeah, okay, yes. That is oh yes. For instance, here I can explain that in this picture, for instance. Okay. Just erase this guy here. Yeah. We see, for instance, here, I'm using, this is the input. This input is coming from real data, fake data, right? And this guy here will, I don't know, will just apply some quantum operations between this guy and the input, between these two guys. This is why the square covered these two wires, because it's doing something to this to these two quantum states. And what happened if I measure something here? If I measure something here, I can get information of what is going on here. In classical computation, is very difficult to see that. In quantum computation, that is quite often. That is called entangling. It means that the state of this wire here, if that stays up, we can infer some information from this guy, from this wire, and then we will know everything about this guy. If I measure this guy here, for instance, if I want to measure that guy, if I need to measure that guy, I will see that guy has been modified because I already measured the first guy, the ancillary qubit, the first one here. That is called entangling. And then this is just a very effective way to store the information, and then you don't have to, you don't need to have a picture of to have the whole picture. You can just extract enough information from part of the system, because if the system is entangled, you can really infer about the rest just from a portion of the system. That's one way of entangling. One way to see the utility of entangling.
Okay, good. I don't see more questions now, so we can continue, I think.
Okay. Yes.
I would have one question.
Oh, okay.
Yes. Sorry. So my question was, I have previously worked on, this work is great, absolutely, but when we were working on a similar problem, we convert the training data into a normal distribution and then sample from it. So so my question was like how this particular stereographic projection is, how good is this compared to the other methods?
That is okay. That's a very good question. Yes, yes. So for encoding, the stereographic projection, as I mentioned before, is a conformal mapping. So if you have the relative distance between the two sets, you have a relative distance between the two sets. That distance, relative distance, I mean the angles between them, if you want to think about that, that will be preserved, but the size of the sets are not going to be preserved. This is why we choose the stereographic projection for this case, because we want to discriminate, but we want just to keep to keep the distance, the relative distance, fixed. And that's one feature of the stereographic projection. It's conformal, yes. I guess that is the meaning of conformality. And also, another feature is the unique correspondence is 1-to-1, and that is actually a very good advantage, because in other methods the correspondence is not 1-to-1. You have to scale. For instance, if you are going to use angular encoding, you know that the angular angles must be in a range between -pi to pi, or 0 and 2 pi, and you cannot go further. So you have just to compress everything in that region. If you use, for instance, normalization has some issues. I already mentioned that. And yeah, then we were looking for into different embedding protocols, and we think the one of the more convenient ones is the stereographic projection, because preserve the relative distance, and it's a one-to-one correspondence.
Yeah, that's now I got it. So maybe I have one simple question over the discriminator. So on the
Yes.
top right hand side of the slide, so there is a, you have told me that the distribution can be seen in a, the difference between the distribution can be even in the any dimension. So that means like our measurement operator has to be in dimension, like direction. For example, here the distance may be found in when I suppose like my measurement operator is usually in Z direction. So if I wanted to see the actual difference, then I need to use like a X operator,
Oh,
poly
yes.
X or poly Y.
Yeah, but since your output must be yes, is how should I say that? You have to discriminate between two quantities. So your output must be close to -1 or close to, okay, larger than 0 or lesser than 0, right? And you can pick any direction. If you want, you can just pick, for instance, I want just to see what is the projective measurement along X, along Z, along Y. And yeah, and then that will give you enough information to just to judge where the input belongs. For instance, where this guy belongs. If it belongs to a real data or belongs to a fake data. And the nice thing of this design is we are using just one qubit here in the ancillary part, because we just need to judge one feature. It is or is not a real data. If you want just to judge more things, for instance, it is or it is not real data and something else, you have to consider more ancillary qubits. And yeah, and this is why, for instance, we use the Z projective measurement, but you can pick a different one.
Yeah, I get it. So there is no like a distance metric used here to
No.
actually do this. Just answer.
I will say this is my frontier, right? And then I want this red spot be over that frontier. So anything belongs to that red spot will be real, and everything belongs to the green one, which is below the frontier, will be fake. That's the effect of this guy. This guy allows us just to, yeah.
Totally got it. Thank you.
Okay, thank you. Okay, my iPad is frozen. Okay, yeah.
Okay, I think there's one more question from Barry.
Okay.
I'm not sure if you want to answer now. Okay.
Yeah, let's go ahead. The last question.
Yep. Okay. Is it fair to say that the advantage of quantum machine learning over classical machine learning is that you can represent more information by adjusting a single qubit state than by adjusting a single classical formal neurons thresholds?
Yes, it is. Yes, a very good point of view. Yeah. Yes. You can store more information. You can manipulate more information, and also I was talking with someone from Lawrence National Lab, and he told me that he has the impression that this kind of quantum machine learning hybrid algorithms it could be more energetically efficient than the classical neural networks, because you are using if you use 10 qubits, you can load a lot of information and keep 10 qubits in the fridge. Is not the same as keep Frontier in the fridge. Frontier has thousands of nodes, and you see the electrical bill is really high. And he told me, yes, keep the quantum computer in the fridge, keep it at a very low temperature. Probably is not as expensive as keep a big cluster, a HPC, under certain temperature, and that could be another advantage.
Okay.
I will,
Yes. There was, I think, one more question on YouTube. I think this is, I'm not sure if it will be short, but I will ask, what is the future scope of quantum machine learning? As this is a rudimentary field right now, should I hope high about this field? So it's a question from Zuber, who is just starting his thesis journey by selecting quantum machine learning.
oh yeah, that's I from my point of view, the quantum computer is better used as an embedded system, and in that way there is a very good potential to use the quantum computer, because the quantum computer has the ability to produce random samples. I mean, real random, and produce samples in a faster than any classical computer. We can take the advantage of the properties of quantum states, and I think I'm quite optimistic on that. I think that would be the next step we should take. Just take the quantum computer as an embedded system. Imagine this: we use GPUs as an embedded system for machine learning, and then you have your algorithm, and then you call your video card just to execute the neural networks, and the video card send the information to the CPU, and so on. The CPU just process that information, and then imagine that you don't have a GPU, you will have a QPU, a quantum processing unit, or you have both, and then you can just send you have your machine learning pipeline, and then one part of that pipeline will be executed by the quantum processing unit. But I'm very positive for that, and I think that would be the future of quantum machine learning, or machine learning, let's say.
All right.
Okay, let me just.
Okay, yeah, I think we
Okay.
can go further. There's a comment from Kevin, but I think there's no questions, so let's move forward.
Okay. So far, this word is a proof of concept. We haven't implemented this yet to any hardware. I will talk about a little bit about the limitations. We have talked about, for instance, the potential to use the quantum computer in a machine learning algorithm. But now let's talk about what are the limitations, why we don't see that already in the industry, and we don't see that working very well. And let me just have this is just so informative. We have different problems. We have to configure, we have to send a signal to the hardware. That signal will represent your quantum instruction, but the fidelity of that signal is compromised by different aspects. It's compromised by the hardware, by the noise. The hardware is affected by the environment. Yes, you have the hardware in a fridge. The fridge is a very, very low temperature, but even though you will have some fluctuations that will compromise that execution, that will compromise the state preparation. If you want just to prepare a quantum state, that noise will really affect that preparation. That will affect the operation. That will affect even the measurement. and there are different ways to see how the hardware how is the hardware performance, and then you can just test the quantum operation by applying a process tomography, which is really expensive. It's really expensive. The scales really bad with the number of qubits, and you can just mitigate. There are some protocols for mitigation, no correction. You can just try to mitigate that using randomized benchmarking, which is also a little bit expensive because you have just to apply randomly gates in a statistical way. You will see some correction at the end. I proposed a parameterized process characterization a couple of years ago, and yeah, there are other protocols that you can apply just to mitigate that. And then just to enclose the FETs, or to enclose the different imperfections, we can say there are two kinds of imperfections. The first kind of imperfections, the coherent ones. It means that there is a problem when you produce your quantum operation or produce your quantum state. From the very beginning in your design, when you just send the signal, in the signal there is a problem, and that is called coherent error. And then you can somehow use a better design. You can somehow correct that. And there is another kind of imperfection, is incoherent. That one is the worst because you can't control that. It's just some effects from the environment that will destroy coherence, will destroy entangling, will destroy different properties, the nice properties that makes the quantum computer awesome. And yeah, this is just these two kind of imperfections we can see in the quantum computer. From the coherent one, you can think, because it's coherent, you can think that this is something that you are not preparing very well the quantum operation, the gate. Let's say you just say, okay, I want to prepare a flip operation, but that is not really flipping. It's keeping some remaining there, or just it's not really perfect. So it's something that you can fix. For instance, you in this little picture is a simplification. Imagine that you have this is your target operation, and this is what you see in the experiment, and you can somehow separate the imperfection from the ideal behavior. And let's say we can put the imperfection on this side or on the other side. It's just a model. And then it means that what happened if in the experiment, remember that this guy is produced by a signal. The signal you send to the quantum computer, this guy is produced by that and has some imperfections. What happens if I can just engineering the signal corresponding to the adjoint operation? And this one is somehow a different signal that represents the adjoint operation of the first one. If you do this, you can cancel out the imperfections. I know it's very simple. It's very simple, and there are a lot of questions behind that. I know, but it's a mitigation protocol. We don't intend to cancel out completely the coherent imperfections. It's just to mitigate the coherent imperfections. And then, for instance, we did an experiment here with a CNAT. This is the one of the most imperfect gates you can find in superconducting qubits. And then what happened, for instance, in a normal gate, if you multiply, for instance, ideally, if you do this operation, you multiply a gate by its adjoint, you will get the identity. It's like doing nothing, right? And then if you do this guy n times, it's like the identity power of n is the identity. It's doing nothing. Okay, and then in principle, if you apply this guy, it's like applying just the CNOT. So in principle, you will see any effects of the power. In principle, ideally, in theory. But what happened in the practice? This guy has errors, this guy has errors. So what you are doing here is boosting the errors. It's making everything worse. And this is what you see here. This is the number, the power. We went until 20. Is a lot of gates. And you see the fidelity at the very beginning. The fidelity is almost 1. It means that the experimental realization of that gate is very good. But anytime you increase the power in this operation, becomes worse and worse and worse and worse because you are boosting the mistakes of every gate. And what happened if instead of using this, what happened if this guy in blue, this guy is just the experimental implementation, and in orange is with the inverse of this operation. We engineer this inverse, and we see, for instance, here when you consider several qubits, several folding, we call this as a folding power, a folding number. We see there is a difference. It means that this guy is better. It means that we are mitigating something, but there is a long way to be perfect, right? It's better than don't using the inverse, but it's still imperfect. And this part here is because there are more things to fix apart from the coherent noise. There are more things to fix, but at least we can just correct a little bit the performance of the CNOT. And then, for instance, here we use different sectors. I guess this is the Montreal. This is a superconducting qubit in IBM. This Montreal, and then we just this operation was done in this sector of the backend. We just move to another sector to see what happened here. We use 3 and 5 qubit. This is the address of the qubit. And then we see, okay, similar behavior. There are some improvements. Some improvements. It's not bad. Until we get this guy. This guy is really, really messy. And then there are some sectors of the quantum computer you can do anything. It just is quite imperfect. There is no, it doesn't make sense, this behavior, because it depends, you know, this is an experimental implementation. There are a lot of things behind that we don't see, and then what happened, for instance, we are going to use this in this algorithm. This algorithm is quite nice. It's used in quantum chemistry. Is used to find what is the energy of the ground state of a molecule, and then you can encode the evolution operator of the molecule in this quantum circuit here. There's an encoding, and this quantum circuit has some parameters. The parameters are these. For instance, these rotations here. These rotations are the parameters. It means that this guy has 3 rotations and has a very nice structure. We have a CNOT here, and we have another CNOT here. And then this guy on the right is being replaced by the emission of this guy. We engineered this guy. We just modified the signal we sent to the quantum computer in order to, instead of send CX, we will send the inverse. And we do the same with these guys here in order to mitigate any possible coherent error that will produce these two guys. And once you have this quantum circuit will produce this quantum state. Look, this quantum state depends on these parameters, the three angles. And once you have the quantum state and you have the Hamiltonian of the molecule, you can compute the mean value of that Hamiltonian, which is the energy. And then you can use the energy as your cost function. And that is something that you want to minimize. And that function is going to be the input of a classical optimization. You can pick any optimizer, Boiqua, Aram, CMA, gradient descent, and then what the optimizer does? Receive a cost function, a value, and say, okay, receive several values actually, and decide, for instance, okay, what would be the best parameter configuration to reduce that value, and then the classical optimizer send that information to the parameterized quantum circuit, and the parameterized quantum circuit will be updated, and we just run again we execute the quantum circuit, we get a new quantum state, and continue with this loop until some criteria meets. I don't know, the number of iterations, the tolerance, and then we apply this inverse here in the design of this quantum circuit, and let's see what were the results in this variational quantum algorithm. The result is here. Using two different optimizers, we use Boiqua, which is a gradient-free optimizer, and Aram, which is a gradient-based optimizer. We were using this in Bogota. It was a backend in IBM, Montreal, Jakarta, and Montreal for the Aram. And see, for instance, this is the learning path. Here we see this is the expected value. This is just the what we are looking for, what we're expecting. This is the ideal value, this E star here. And in blue is the simulator, the noiseless simulator, just to prove that the quantum algorithm will work if we don't have any noise. Yeah, that is quite necessary. You don't know if you need simulators because you need to test your quantum algorithm to see if that really works or not. And yes, and this is a test, and yep, converges to the minimal energy. We already know that energy is H2. It's a very well documented value. And this is, for instance, in orange here is the default without making any change in the quantum circuit, just using the synapse as is. And we have the hidden inverse, as we call that method, when you just insert some inverses into the quantum circuit, is in red, and in green, the randomized compiling, a very powerful method you can use to reduce the coherent imperfections. And you see the hidden inverse in the randomized benchmarking has a similar behavior, but the hidden inverse is quite cheaper because I just have to change a couple of synapses by their inverses, and that's it. And you see here is the same behavior, randomized compiling and hidden inverse. Here is really good. And yeah, then this is one of the very nice results, how we can just mitigate coherent errors. And this is another example of a hybrid classical quantum algorithm where you can just learn something. In this case, you are going to learn what are the parameters for this quantum circuit to generate the ground state and also the energy. Is there any question about this?
Okay, let's wait and see. I don't see questions on our chat now, but
Okay, let me just clean this mess. Okay, and then
go on.
And then, for instance, I mentioned before that we need simulations because imagine that you design a quantum circuit. You design a hybrid classical quantum algorithm. How do you know that that quantum algorithm will really work? You need to simulate that. You need to simulate the execution of your quantum computer. You need to a noiseless quantum computer. Also, you can, if you want, you can just simulate the noise effects in order just to see how robust is your quantum algorithm against imperfections. Some algorithms are really robust, and it doesn't matter what is the what are the imperfections. You will still get in the correct answer. And this is why we started with a verification protocol in Oak Ridge. Here is the publication. If you want just to have a look at that, we consider, for instance, a verification of from the simulator. How is the noisy or noiseless simulation in comparison with the hardware implementation? And for instance, what are the conditions where the hardware will just give you nonsense data? And then, for instance, we apply this in another variational quantum circuit called variational quantum algorithm, hybrid quantum algorithm called quantum approximate optimization algorithm. The nickname is QAOA. I know it's quite famous algorithm where you can just solve these kind of graph problems when you have some nodes, and then you say, okay, what is the mascot I can produce in this kind of graphs? And this algorithm will help you with that. Will give you what is the best cut you can have. And we test this in different shots. There's here the relative error and on hardware and on the simulator. This relative error is with respect to the simulator. Sometimes it's very high because if the number of shots is very low, you see the relative error is really high. You have to consider a very high number of shots if depending on your application. And then with this verification protocol, you can just define where is that limit. Okay, just to end the presentation, we have talked about, for instance, what are the different applications, some applications and the quantum solution to those applications, right? And now, for instance, we mentioned a couple of some slides before in a question when I was answering a question about the interface, the standardization of this interface here. There is no any standardization. Every platform has their own language. They have their own way to define the quantum instructions, their own way just to send that quantum instructions to their hardware. Ideally, it would be nice to have on standardization, something that we can use without any transpilation, any extra compilation effort. But for now, we can use the XACC. In XACC, you can have from a very high level. I mean, for instance, you can just use different language, OpenCASM, Quill, Qiskit, Penny and other languages, and you can write down your quantum circuit. You can embed your quantum circuit into your quantum algorithm, hybrid quantum algorithm. Now imagine that you are using Qiskit language, Qiskit syntax, and you want to run that, I don't know, in Rigetti. And for instance, if you if you don't have any of these tools, what you have to do is translate all your code into Query. All the functions you have defined in your code has been translated, has been transpiled. So XACC has a way to do that. Whatever you put into XACC will use a intermediate representation of that, will generate that, and will process that intermediate representation again into any vendor's language. So it doesn't matter if you start with OpenCasm and wants to execute that in Rigetti. What you have to do is just tell to XACC, I want to run this code in Rigetti, on Rigetti. Yeah, that's it. And this is a nice feature. Now, Microsoft, NVIDIA, and other organizations, I'm thinking about this, the intermediate representation, but take that intermediate representation to take that or convert that intermediate representation into something standard. So the vendors, I mean, with the vendors, IonQ, Rigetti, IBM, D-Wave, they will use that representation into their platforms. So that will be nice for the standardization. And this is called, where I put that? The quantum intermediate representation protocol. And NVIDIA, Microsoft, Oak Ridge National Lab, along with other institutions, are working to bring a standardization in the quantum program. You can just have more information about that. Just put on Google quantum QIR Microsoft, and you will see all the documentations and the history behind that. Okay. Let me just finish the presentation. What we are doing right now, we are still working on the quantum embedding, exploring new methods to represent classical data into the quantum picture. We are also improving the quantum classification part. We are using different metrics based on the quantum feature information. We are also working in the integration of Frontier AMD GPU system. They have an AMD system. How is the integration of Frontier with quantum simulators and quantum hardware? And also, we already work on the correction of coherent errors. But as you remember that we just mitigate a little bit the imperfections by correcting the coherent errors, but there are a long way to be perfect. And this is why we started with the study of the decoherence characterization. So if we know how is the decoherence of the quantum computer, we will know how to mitigate that. Okay, that's what I have for today. And thank you very much. I'm just open for questions.
Great.
Thank you.
Great. Thank you. Thank you, Vicente. All right. Do we have more questions? Jordan would like to ask.
So in terms of on the horizon here, what do you estimate timelines for a practical real QRAM to be, usable? Do you even see that on the horizon?
Yeah, yes, I know what you mean. Yes, everybody, that is a common question, Yes, everybody, I mean, the investors, in principle, are asking for that. When am I going to get my money back? I think I'm quite optimistic. I think 5 years or less, because now, for instance, there are a lot of efforts in compressing the number of physical qubits you need for a one digital qubit. That number now is not huge, and in Quantinuum and Rigetti, IBM, everybody is working really hard just to make everything more reliable. I can tell you 4 years ago, or more than 4 years ago, I don't remember now. I remember we used to receive some notifications from the vendors. Don't use this qubit. Don't use this INAT because it's really messy. Don't use it. This sector of the quantum computer is bad. Use that sector. And then every time we were using the quantum computer, it was really bad. The output, we were happy because we were getting something. But it's not really comparable to the things we see right now. You can see very clean radio oscillations. You will see fidelities over 99 percentage. You will see, for instance, coherent times over a second is really crazy, and you will see, for instance, a very nice connectivity between the qubits, a lot of qubits. Yeah, I think the field is growing so fast, and then I think probably in the run of 5 years we will see something really nice coming out. Something not nice, something useful.
Thank you. Yeah, that's the key. Useful, that we could start.
Yes.
Okay. Do we have more questions? Oh, there is a question from Peter. I think it was regarding the previous slide. Is that pure quantum or hybrid quantum classical? But Peter, maybe you can clarify which.
Yeah, the representations at the beginning and at the end. Is that pure quantum algorithms or?
No, yes, that's a very good question. Yes, they are hybrids, because here in the QIR, in the QR representation, the intention here, the intention is to have classical instructions and quantum instructions. And then let me just give you more details about that. We plan to use LLVM, low level language, just to represent the quantum circuits. So that allow us to configure the execution engine. So in the low level language, you have, for instance, some classical instructions, and you can send these because you can customize everything. Then you can say, okay, if I have a classical instruction, I can execute this part of my algorithm in this AMD processor on this Intel or whatever. Or if there is a quantum instruction, I can send this instruction to a quantum computer or a quantum simulator, because you already have your execution engine there, and then you can just delegate instructions to different architectures. And LLVM is quite popular because you can optimize your compiler. There is one nice feature, is the running time compilation. Usually what you have in the normal Lexer structure, you write down your algorithm classically, or in the quantum picture as well. You write down your algorithm. You send this to a Lexer. The Lexer just do something there that you will not read it. It's unreadable because it's just a compilation that will translate that into a machine language. But you have to pass all the code from the beginning to the end to the Lexer. The Lexer will just produce something else, and then that thing is going to be run in the processor. But in LLVM, you can have a little piece of the code and running time. Send this piece to the processor and wait for the output and run and just execute the next line one by one. That's called running time. and you can do that, and then you can send that to the processor, to the classical processor, or to the quantum processor, and wait for the output.
Yeah, this is great. This is very exciting to me because we've been in the quantum assembly era for several years now, and it's time to move on to the first generation languages and settle on something that's a little more programmer friendly. Not everyone is cut out for assembly language programming.
Yeah. That's yes, and it's not easy. I can tell you, this has some challenges, and yeah, we are working on that.
Thank you so much. Yes.
Oh, thank you for asking.
All right, good. We have some more questions. Itamar?
Yeah, as we see so much advance in all aspects of quantum computing, I'm curious about the old tools from engineering, looking at devices in terms of reliability studies and fault tolerance. That's related to errors, but it's earlier tools.
Can you rephrase your question?
I'm wondering if anybody is looking at fault tolerant of these devices and reliability studies or reliability tests of the algorithms, the devices, the coherence, the error in those early, maybe ancient now or retard now tools, but I think they're still having some role.
You mean if there is an intention to benchmark the quantum computers in using some algorithms, some verification algorithms?
No, what I mean is beyond this discussion, I don't hear anything about reliability studies, which is there are courses in engineering about and books about reliability as a science, as a toolkit. And then there is fault tolerant, namely you build one system and maybe there is a backup system in case something goes wrong. I mean, these physics devices and approaches are quite delicate.
Yeah.
A lot of things can happen there beyond just noise, that can be handled somehow.
Oh, that is a very interesting point. I haven't heard about that, but that is quite interesting. I think that could be the next step.
There's so many next steps, but anyway, thank you very much.
Okay, no, thank you for bringing that up. It's very interesting just to.
Great, perfect. And one more question from Sabari Kirishwaran. So please ask.
Yeah, thanks for. So my question is about as you have shown this XI, that architecture that people are working on, then how about the efficiency of the code execution? Like, so every hardware they have their optimized assembly language. So how we are gonna overcome that?
Yes. Yes, that is a very good question. Yes. You mean, for instance, yes, the efficiency, AOLBN is quite famous for that because of the efficiency. The running time execution is quite fast. I can give you a couple of examples in the classical picture. For instance, one of them is Mojo. Mojo is just a programming language that is expressive as Python, but is really fast. It's as fast as C++ because of the low-level integration, the running time protocol they apply. They are using AOLBM just to execute the algorithms. And in the QIR, we are using something really similar. The problem, there is always a problem. The problem is the connectivity with the quantum computer. There is not any problem with the classical processor, because you usually use that with your local processor. But the quantum computer is not really integrated physically to the system. You have just to use also network protocols. And one way to mitigate that is what LZR in Germany. There is a company that has a HPC system and a quantum computer on site, and then they have the quantum computer next to the HPC. In that infrastructure, you will not see any delay. That would be optimal, but for that you have to build your quantum computer next to your HPC, and that is quite difficult.
Yeah, I get it. So how about this QIR also include analog computing?
Yes.
Analog quantum computing? Or
no.
okay.
Wait. No, that is in the schedule. Yes, we are going to integrate pulses, and after that, analog computing. Right. I'm sorry. Yes. That is a very good point. Yes, that is on the that is on the schedule. There are a lot of things to do, but yeah, that's very important point.
Yeah. Thank you. It looks like a very large scale project. Thank you.
Thank you.
All right. And do we have more questions? Oh, there are some acknowledgements, comments on our chat. So I see that people are really satisfied with the meetup today. All right. I don't see more questions now. Maybe last chance to ask. Okay. I think we can finish for today. So, Vicente, thank you once again for a great talk and for answering all the questions. It was very interesting and fruitful discussion. I believe that we've learned a lot, and
I
yeah.
learned a lot. It was
As
really
well.
really interesting. Yes. You know when you sometimes questions take your side to another angle.
That's true. I agree. So you can
Force
always
you
learn
to
from questions.
yes, because force you to think differently, and then that is really fruitful.
Good.
Thank you, everybody. Thank you for the attendance. Thank you.
Actually, there's one more question from a participant.
Oh,
How
yeah.
do you deal with large number of data needed for ML?
Oh, what?
How do you deal with large number of data needed for machine learning?
No,
There's one more question from Sasu.
How I think no, I don't understand that.
I think it's a question related to classical or maybe also quantum, so to machine learning in general. How do you deal with large amount of data needed for machine learning?
No, because sometimes you don't need all the information you get from the observation. Sometimes you have just to apply some feature engineering. You have just to extract some features. And I use, for instance, the principal component analysis, and that will give you good enough information about the correlations you can find in the real data. Usually, you don't. I don't know if that is. I'm not really an expert in classical machine learning, but what I heard is you just you apply some feature engineering to extract the information, the main information from the data. This is how, and also regarding with qubits, sometimes you don't mind, because for instance, if you are going to use 10 qubits, now there are machines with 140 qubits. If you use, for instance, just 10 qubits, you can store 2 to 10 items in the quantum state for 10 qubits. That's a lot.
All right. Good.
Okay,
Yeah,
thank you.
Thank you. I don't see more questions. So Helen, I think we can finish for today. So we
Okay.
also thank everyone for coming. Oh, there's one more question from Jervis. Are there publications on this topic? Which topic exactly you have in mind? Because about quantum machine learning, there are many publications already. There are even conferences and workshops on quantum machine learning. So there are a lot of papers. But maybe you have some
Yes.
specific area.
I can tell you there are. The other day I was tracking that. It's almost 100 publications per day.
Mm-hmm.
It was a few months ago. There was a peak in the number of publications. I don't know. I stopped tracking that.
Mm-hmm.
Because there are a lot of publications in this field. There are a lot of things. It's very difficult just to keep aware about what is going on everywhere. It's just really difficult.
All right. Yeah. So if you are asking about general quantum machine learning, then there are many publications. There are already books. There are massive open online courses about quantum machine learning. So there are many places to learn. Yeah, good. All right, Helen. I think that now we can finish. So we thank once again all the participants for coming. We hope to see you next time in March and during our next meetup. And Vicente, thanks once again for this great lecture and discussions. And we hope to see you next time.
Thank you.
Thank you.